want to talk about something else you could do with functions, and it's it's called composition of functions. And this is like the operations we were talking about on sets and logical statements, where you take so in this case take two functions and it gives you another function. But they're not functions, any two functions. They have to be compatible in some way. So let's use this notation to be more suggestive of what we want to do. And y to z. So let's call this g. Okay. Be two functions. Okay, so they're not arbitrary because we're requiring that the codomain of f is equal to the domain of g. Right, so these have to match up, and the function that you get denoted f circle g is the function that goes from x to z, and it's exactly just from joining the arrows together. So, and in the way it's done, it's kind of x to y to z by g. Okay, and so what happens for x is it goes to g of f of x. Or here you could see how x kind of goes to f of x, and then it goes into g of f of x. Okay, so that's kind of a natural thing to do with functions. So if you can line up the inputs here to the outputs there, you can output it again, and that's the composition of functions. I want to talk about inverse functions, and to do that I want to introduce first some notation, this ID x. So if x is a set, x and y are sets, then this ID x is a function from x to itself, and it simply takes every input to exactly the same thing as its output. Call that the identity function on x. So if we have two functions, one is f from x to y, and another one g from y to x, then we say f undoes g. So this is a phrase, f undoes g, if, well, basically after doing f you do g, then the result was nothing that was done. So you do you do g first, no, sorry, I mean f undoes g if you first do g and then you do f, and then it's as if you did nothing. Okay, so that's what undoing means. So if you do g first, y goes to x, and then you do f, goes back to y, then this is equal to the identity on y. Okay, so another way of saying this is g composed with f. And you can create a symmetric thing for f, for g undoing f. This is f undoing g. Okay, we say f and g are inverse functions. if f undoes g and g undoes f. Okay. And a given function may not have an inverse function. A given function may not be able to be undone because it might have done something so irreversible that there's no way to undo it. So if you have a function that sends all its inputs just to the same output, there's only one output for all the inputs, you can't undo that because you've lost all the information about the inputs because they all have the same output. Okay, so the main result of this is, I'm going to actually label it, the theorem is, so let f be a function and f has an inverse if and only if, or if and only if f is bijective. Okay, so hopefully we can try to show or prove this statement on our own before seeing what the actual proof looks like. I'll leave it there for now.